So far we've been dealing with scenarios where the fluid has been at rest, and when we've been looking at the effects that either pressure or force from that fluid have on an object. Now we're going to talk about what happens if the fluid is in motion. So I've drawn a subsection of a pipe here where area 1 is larger than area 2. And we have an equation called the equation of continuity that's going to explain what happens to the net motion of the object as we go from area 1 to area 2. And this is the equation of continuity over here. So area 1 times velocity 1 is going to equal area 2 times velocity 2. And this is going to go hand in hand with something we refer to as Bernoulli's equation. So Bernoulli's equation says that P1, which is often atmospheric pressure, plus 1/2 rho V1 squared, where V here is the velocity, plus density of the fluid times G times height 1 is equal to P2 plus 1/2 times the density of the fluid times velocity 2 squared plus the density times G times height 2. So this equation is actually derived from the conservation of energy formula. So you'll notice the shapes of the equation looks very similar, where we had V squared with kinetic energy and height with gravitational potential energy. So if I would have derived this from first principles, I would have started with the conservation of energy equation. This velocity 1 here is this velocity 1 down here. This velocity 2 is this velocity 2 down here. And so we can use these equations together to establish what happens to the pressure of the fluid as you go through a different sized pipe and the velocity changes. Alright, so here we have a fluid and the individual particles in the fluid are represented by the dots. Before I do anything to this, and what I am going to do is I'm going to narrow a section of pipe, I want you to, in your head, decide what's going to happen to the velocity of the fluid flowing through the narrow section of the pipe, and what's going to happen to the pressure in the narrow section of the pipe. So I want you to commit it to an answer now before you actually continue watching the rest of this video, because it may not work out exactly the way you think. Alright, so hopefully you made your decision about the velocity and the pressure in the narrow section of the pipe. So first I'm going to narrow the section of the pipe and already visually see what is happening to the speed. So if I take out my speed probe, here we're at about 1.6. And here we're at about 6.2. Now I'm going to take out a pressure probe and put it at the same spot. So we're a little bit under 118 kilopascals. And what's usually pretty shocking is the idea that the pressure is actually decreased. So whenever you increase the speed of a fluid flowing, and a fluid could be, in this sense, both a actual liquid and a gas. Whenever you increase the speed of the fluid, the pressure actually decreases. So it's a little bit counterintuitive to what you might have thought before.